Hello again and welcome to the 6th video on integration for Year 13's Edexcel Maths course for A-Level. So let's have a look at this chapter, which is going to be talking through a method for integration which is known as integration by parts. It's a massively crucial method, maybe one of the harder ones, but one where you can almost guarantee in some form or other it will crop up in the end of year exam. So let's get to it. And I'm going to show you a method called the DI method for tackling this. I'll make a second video showing you the traditional method. So I'm leading with what I call the DI method. I found it online from a different channel. I don't mind admitting this. It was from Black Pen, Red Pen, a guy based in, I think it's California or Berkeley. In my opinion, the guy's a genius. So if you really want to push on for A or A-star grades or are considering maths at university or just love maths, check out Black Pen, Red Pen. I'll put a link in the description below. Very high-powered stuff, and keeps me on my toes, to say the least. Anyhow, before we get started with the main bit, we need to get warmed up. So I've picked two questions here. The first one is stats, the second one is trig. Press pause, try them on your own, and when you're ready to see the solutions, press play, and I'll talk you through how to tackle them. Assuming you've done that, let's have a look at question one. Question 1 is about a nursery which has a sack containing a large number of coloured beads, of which we're told 14% are red. Alia takes a random sample of 18 beads from the sack to make a bracelet. Part A, we need to state a suitable binomial distribution, so we're told it's going to be binomial, to model the number of red beads in Alia's bracelet. So we can let X be the distribution, and what I'd suggest we do first of all is let's just call X B for binomial. The first parameter is a number of trials, so if she's taking 18 beads, that's going to be 18 beads. The second parameter is P for probability of the event happening. So 14% are coloured red. There's going to be a 0.14 chance of picking a red bead. Part B, we're now going to use this model to calculate probabilities. So B part 1, we're going to calculate, using this model, the probability that Alia has just picked one red bead in her bracelet. So what we're going to do, we're going to get the calculator up and ready. Different calculators will do this in different ways. The Casio ClassWiz, this version is my personal favourite. So we're going to go to menu, distribution, going to go to binomial, and this time because we're trying to find an exact probability, just one bead, I'm going to click binomial PD, which is number 4, and then I'm going to go to number 2 for variable. So I want to work out the probability of picking 1 out of 18, so big N is 18, where the probability of picking a single red bead is 0.14. Press equals and equals again. That generates a probability of 0.194. So that's our answer for question B part 1. So part 1, probability of X taking the value of 1 is 0.194. Part B, part 2 is slightly different. It says, what's the probability that there's at least 4 red beads in Alia's bracelet? This one here is different because we need to work out now the probability of X being at least 4, so we need to use an inequality. The calculator generates probabilities leading up to and including a certain value. It doesn't work out a value or greater. So what we need to do is to think of this in a different way. The chance of the number of red beads being 4 or more, that's going to be every single possibility you can imagine. That's a 100% chance, apart from, of course, the probability that she picked 3 or less. So we need to do this step here to work out the chance of what 4 or more would be. So 1 minus the probability of X being less than 3. This time, because it's an inequality, a range of values we're interested in, 0, 1, 2, or 3. We can go back to the calculator, but this time we can change from it being binomial PD to binomial CD, which is the cumulative binomial distribution, because after a range of values all the way up to and including 4, rather up to including 3 is what we're working out. So press 2 for variable. So what's the chance of getting 3 out of 18 or fewer if the p-value of just getting one of them is 0.14. Press equals. We get 0.0 0.7618, blah, blah, blah. So 0.7618, etc., etc. So I need to do that calculation now, 1 minus this. So, go back to menu, normal mode. 1, take away the answer I just got, gives 0.238. So that's B part 2. Part C, we have to comment on the suitability of a binomial distribution to model this situation. Well, one of the things we need to hold for a binomial model to be appropriate is that the probability of picking a red bead, or generally speaking, the probability of an event happening, needs to be fixed for each trial. So here, each time we pick a red bead, that will actually lower this percentage. So it's not going to be a perfect fit for binomial. However, it could be a pretty decent fit if you're talking like thousands upon thousands of beads, for example. If 18 beads are taken out to make a bracelet, then the more beads you have, the more it's going to be like a drop in the ocean in terms of affecting the overall picture. So the more beads, the better. It won't affect this 14% too much. But for example, if there were only, say, 40 or 50 beads in the bag, picking 18 out would be hugely significant. So it's a bit awkward to word. This is the best I could come up with. I'm not saying this is perfect by any means. So I'd say something like a binomial model could be suitable if the number of beads is very large, such that removing 18 beads has a negligible effect on the proportion of red beads still inside the bag. Something along those lines should pick up the mark for you. Moving on towards part D now. After several children have used the beads from the sack, the nursery teacher decides to test whether or not the proportion of red beads in the sack has changed. She takes a random sample of 75 beads and finds 4 red beads. So, stating your hypotheses clearly, use a 5% significance level to carry out a suitable test for the teacher. So, there's going to be hypotheses, that's plural of hypothesis. So we're going to have H0 and H1. In fact, I'll put H1 on the top line as well. Never mind, I won't. So H0 is assuming that nothing has changed. This is called the null hypothesis. And so if nothing's changed, I often think of the null hypothesis as well as being innocent till proven guilty, if you like. Assuming nothing's changed, assuming what you've told has been true, unless there's evidence to the contrary. So what we're told here is that 14% of the beads are red. So H0 is, that's going to still be the case. So we can assume the probability of a red bead is going to be 0.14. But what's happening here is we want to see whether or not the proportion of red beads in the sack has changed. It doesn't say if it's changed on the large side or gone lower. It just means, is it different? So this is actually, without quite saying it, a two-tailed test. So our alternative hypothesis, H1, is now P is simply not a 0.14. And so we can imagine this as a binomial distribution now. So if I just sketch on a bell curve like so, where obviously at the top is going to be 75 beads, down at the bottom end is going to be 0. And it says here that from 75 beads, she's found only 4. What I'd always tend to do is think about what the mean would be, or the most commonly expected value. If there were 14% coloured red and 75 are picked, we'd expect the peak to be at 14% of 75. That would be what you'd expect to happen. So what would that be? So 14% of 75 comes out as 10.5. So you'd expect 10.5 red beads, typically. Here, though, only 4 have been actually selected or picked out. So what's actually happened is only 4 have been picked. I always tend to do this so you can imagine and see quite clearly which tail you're looking at. We're looking here at the lower tail. So what was the chance of that actually happening? What's the chance of getting 4 or less? So probability, assuming H0 to be true, of X taking on a observed value of 4 or less, we can now calculate. So menu 7, CD, because we want in a range, a cumulative probability from 0, 1, 2, 3, or 4. What's the chance of getting 4 out of 18 if the probability of picking a red was indeed 0.14? So Daisy, what have I done here? So 4, not out of 18, my bad, it's 75 in this question. I thought it seemed a bit strange. 4 out of 75, apologies. That gives a value of 0.0151 approximately. So this here represents a probability of 0.051. We can now compare this to the level of significance for our test. So that's 0.0151. But we wanted to test it at a 5% level of significance. 5% significance level, if it's a two-tailed test, means that we consider this significance split into 2 evenly across both tails. So 0.0151, that's about 1.5%. So that's a tinier bit of a tail than what 2.5% would be, because 2.5 is half of 5. 2.5% would be a bit more than 1.5%, so would therefore be covering more of this tail. So 2.5% in the higher tail would be something like this. 2.5% in the lower tail would be like this. So we can see that the observed value of 4 is within the critical region. So we can conclude here by saying, because 151 is less than 0.025, the value is significant. So therefore, we're going to reject H0, and we can conclude the proportion of red balls has changed. Not balls, sorry, beads, it's saying. So reject H0, proportion of red beads has changed. We can now start to consider part E. So part E, we need to find the p-value in this case. The p-value in plain English just means the probability of an observed value taking that actual value. So what was the chance of getting 4 or less? It was 0.051. Anything we need to do now, if it's a two-tailed test, we use a symmetry and multiply that by 2. So the proportion here in both tails for symmetry would be 0.0151 multiplied by 2. So 0.01506 or whatever it is to be more accurate. 0.0150 multiplied by 2. So that's the answer. Go back to normal calculator mode. So my answer multiplied by 2 is 0.0301. So I'm going to write this down, and that's essentially my answer. So 0.0301. This is another way to illustrate that our test was significant, because this represents 3%, which is lower than the level of significance. So therefore, considering this option here, that's therefore significant as a result, because 3% is less than 5%. Let's have a look at warm-up question 2. Question 2, we need to solve theta for the interval from minus 180 degrees up to positive 180, the equation 9 sine 2 theta equals 16 tan theta, giving answers where necessary to 1 decimal place. So first off, we need to spot here that we're not talking in terms of the same stuff. We've got a 2 theta here and a theta there. So what we could probably do with doing is changing sine 2 theta in terms of sines and cosines using the double angle formula. So if I just rewrite this now, there's 9 lots of 2 sine theta cos theta, just switching sine 2 theta for its identity here. That gives 16 tan theta. And here for tan theta, I'm going to rewrite it in terms of sine and cosine. So that's 16 times sine theta over cos theta. So it might be tempting to think I've got sine on both sides, let's divide through by sine theta. When it comes to A level, and especially trig, try to solve by factorising rather than dividing through. If you divide through by sine theta, two things might happen. You might lose a solution, and also, for all you know, you could be dividing by a 0, which is a big no-no. If sine theta were equal to 0, for example, if theta were 0, and look here, 0 is in this range, so definitely don't be dividing by variables, instead try to factorise. So you can't divide by variables, but there's nothing to say you can't multiply by them. So to undo this being over cos, my suggestion next is to multiply both sides of this by cosine theta. So on this side, I'm going to have 9 times 2, which of course is 18, sine theta, cosine times cosine gives cosine squared, and over here, I'll just have 16 sine theta. Now, I'd get it all to the left-hand side by subtracting 16 sine theta from both sides. That then gives me 18 sine theta cos squared theta minus 16 sine theta equals 0. We can now factorise, and also we could divide through by 2, because 18 and 16 are both even numbers. So we can factorise out sine theta, and because that's going to go to 9 and that's going to go to 8, I can then include this in the working. So I'm going to have sine theta, brackets, then that's going to give me 9 cos squared theta on the inside, and then I'm going to go for minus 8 here, because obviously I've divided through by 2, I'm going to have minus 8 equals 0. So because we're going to be solving a trig equation, and my preferred way is a cast diagram, I've just got one ready here. So one thing we can now do, if I just section this out because I'm running out of space ever so slightly, you need to consider how this can be solved. That is not a straight line. That's a bit better. So it's either sine theta is equal to 0, or this here is equal to 0. So sine theta could equal 0, or it could be the case that 9 cos squared theta minus 8 equals 0. This one's easier to solve. If sine theta is equal to 0, you could actually do this using your calculator, to be fair, or just know it, to be honest. You should know that sine 0 is 0, and using the properties of a sine graph, sine 180 is 0, and indeed sine minus 180 is 0. You could use a cast diagram if you really wanted to. The principal value would be 0 degrees, so using the cast diagram, that would just be these axes. So the axis is going to be on the 0 lines, and to get to 0, it should be 0, or turn around and do 180. So from this one here, we've got solutions which are going to be the following. So if sine theta is equal to 0, in this range, from minus 180 up to 180, we can say therefore theta is going to be minus 180 degrees, could be 0, or could be positive 180 degrees. On the upper end, not on the upper end, sorry, this one here, 9 cos squared theta minus 8 equals 0, needs rearranging. And so if I add 8 to both sides and then divide by 9, I see that cos squared theta needs to equal 8/9. Square root both sides and consider plus and minus. Cos theta needs to be plus or minus the square root of 8, which is 2 root 2, over the square root of 9, which is 3. Again, not enough space. I seem to be very good at doing this. I'll never learn my lesson. So we can take the principal values for this. So we can do cosine minus 1, 2 root 2 over 3, which gives 19.47. The minus option is 160.53. Obviously it says to give it to 1 decimal place though. So from here, I can say that theta is either going to be, it was 19.5 to 1 decimal place. I'll do the other one in a moment. So 19.5, if we just use a cast diagram, then what I can say here is 19.5 will be there. So call that 19.5 each way round. So theta could be 19.5. And here, considering the positive 2 root 2, if theta is positive, I could also be looking in this bottom quadrant as well. So I can have theta being 19.5, this one, or because we can have positive 2 root 2 over 3, we can also have cosine being a positive thing down here, and we can have negatives in our range. So we could go to minus 19.5 as well. So from this one, theta is 19.5 degrees, or minus 19.5. And from the minus option, minus 2 root 2 over 3. Again, just checking the calculator to show you, we had 160.5. If you notice here, 160.5 plus 19.5 adds together. So actually, weirdly, this is still the same angle. So if theta is negative, then theta could also be along here. So it could be in the S quadrant, or it could be in the T quadrant. So that way round is 160.5. I can't go to T going this way round, because that would be more than 180 degrees, which is outside of a range. So to get to this one, I'd have to go that way, which would be minus 160.5. So the two options where theta is plus 2 root 2 over 3 are those two, and where theta is negative 2 root 2 over 3, I've got 160.5 and minus 160.5. So putting them all together, all the solutions, I've got these 3 for sine theta being equal to 0, and these 4 from cosine theta. So for part A, the full solution is as follows. So A, we've got theta equals, could be as low as minus 180, could be minus 160.5. In fact, I'll get the red line ready so I can underline my answer. So it could have minus 160.5 degrees. Could be minus 19.5 as well. Could be 0. Could be positive 19.5. Could be positive 160.5. And finally, because we're up to 180 inclusive, it could also be 180 degrees too. So that's a full range of what theta could be. That's a full solution set. Part B, it says to deduce the smallest positive solution to the equation 9 sine 2x minus 60 equals 16 tan x minus 30. So the best way of considering this, I think, is to consider it as a graphical transformation. So essentially, this here, if you consider this to be f of x and g of x, in terms of graph transformations, then this here, it's like, call it theta rather, because it's in terms of theta, not x. This here, 2x minus 60, and especially here it's easy to see, this is a function of g, theta minus 30, or x minus 30 now it's saying. So what's happening is every entrance of theta has been replaced by x minus 30. If you remember graphical transformations from A-level and even GCSE, inside, opposite. In other words, it looks like we're going to subtract 30 from each of these solutions, whereas actually we add 30 to the solutions. So make the solutions for theta 30 bigger. The smallest one which will pop out to be positive will be this minus 19.51. And so we take minus 19.5 and then add 30 to it, and we get 10.5 degrees to 1 decimal place. Now that we've tried these warm-up questions, let's make a start on the main body of the lesson, which is integration by parts. Integration by parts then. What is it? Why does it have this name? Well, in chapter 9, which was differentiation, if you recall, we saw that an algebraic product can be differentiated using what was the product rule. So to summarize and take you back to that, the product rule says that if you're trying to differentiate a product with respect to x, where the product is some function u of x multiplied by some function v of x, then we can simply take the product of u multiplied by the derivative of v, then add to that the derivative of the function u multiplied by the function v. We can now make uv prime, or uv dashed as I sometimes call it, the subject of this by subtracting u dashed v from both sides and then putting uv dashed first. So we can see that uv dashed is the derivative of uv minus u dashed v. What we could do now is integrate both sides of this equation with respect to x, and this result leads to what is known as integration by parts. So it's by parts because there's two different parts to it, and if we just integrate both sides, we'll get this result. So uv dashed becomes integral of uv dashed dx. The derivative of uv, if we integrate it, we'll just get uv back itself, because integration undoes the differentiation here. So we just get the product of u and v. And then minus u dashed v becomes the integral minus the integral of u dashed v with respect to x. So this is a crucial result, one of the biggest in the entire course, in fact. We use integration by parts when we have a product of two functions that cannot otherwise be simplified or manipulated into a function we are able to integrate using any other method we know. So if we need to integrate a product of two functions when there's no obvious simplification to see and a u substitution doesn't seem to work, then in almost every other case, this result here, integration by parts, is the technique we need to be using. So, what to set as u and what to set as v dashed? So as we can see, to use the integration by parts method, we need to be able to differentiate one of the functions and to integrate the other. So u is a function we need to first differentiate to get the u dashed from the u. So we can simplify this question by just considering only the function u. So in other words, if we can just figure out what to assign as u, we therefore integrate the other function, and the other one must therefore be v dashed. So just let's focus on what to set as u. Luckily, there is a decent mnemonic for this. So that's layat, and because we don't use inverse trig functions, which is I, you could get away with just saying late. So remember late, or layat, to be full. So what on earth is layat? L stands for logarithms. So this is what you'd prioritize u first and foremost. So if you see any logs, if one of the products is a logarithm, in other words something like ln kx, that's what you set as u. Next on the list of priority is inverse trigonometric functions like arcsine kx, arccos kx, arctan kx. As I've said, you don't normally need to consider I, but I'm going to put it in for reference because it might be that you're a further mathematician or just interested. So I've included I anyway. After I, the A just stands for an algebraic expression, for example, x squared plus 1, x to the minus 3, or some polynomial function. T stands for a trigonometric function, so sine kx, cos kx, tan kx, and other standard results, and by standard I mean the things found in the formula book, which you would be expected to know. And last but not least, the last thing ever you'd want to set as u is an exponential. e to the power some constant multiplied by x. So just to explain again, we assign u as a first type of function found on the above list, then therefore the other function we therefore assign as v dashed. And also, like I said earlier, you don't need to integrate inverse trigonometric functions on this course, so I've just included I, the full acronym LIAT, for reference only. So now I'm going to explain and give to you a method called, well, what I call anyway, the DI method, which, as I mentioned in the introduction on the video, I found this online. I was doing my research. Is there any easier way for this hard topic? I do believe I found the best way ever. I don't say that lightly. I think this is an absolute game changer. That said, it's not the way I was taught, so I will include another video using the more traditional method. I almost feel guilty and like I'm being bad against my old teachers and pretty much every other teacher I've seen. I'm not knocking the original method at all. I'll make a separate video for that. But flavour one, I'm going to show you here the DI method. So what on earth do I mean by DI method? It's a process essentially. So what we can do is we create a table like the one on the right, hence DI. So down the side we're going to put alternate plus, minus, and the signs here are attached, if you like. You can think of a plus relating to the D column. Use as many rows as is needed. Typically 4 rows will be enough. So plus minus indefinitely. I'll never see an A-level question, I don't think, where you need more than 4 rows. In fact, 3 I think is pretty much the maximum. So what does D stand for? What does I stand for? You can probably guess, but essentially in the D column, in the first row, you put down U, and that's a function to be differentiated, hence D. And we assign D according to the LIAT acronym. In the I column, in the first row, we write the v dashed function. In other words, v dashed is a function we're going to integrate. In the next rows, we keep differentiating the D column and keep integrating the I column entries, stopping only when we reach a row that can be integrated, or when you see a row appear that is some multiple of a previous row. If either of those happens, that will be your final row, and you don't need to go any further down this table. When you get to the final row, as well, we multiply the D and I entries diagonally downwards until you end up multiplying an entry that sits in that final row. Then finally, the final row itself, we just find the integral of a product of the two expressions in that final row. On its own, I don't expect you to make much sense of these instructions whatsoever. I certainly didn't. I had to watch a few examples be done, and after a few examples, you'll see hopefully just how easy it is. So rather than giving 2 or 3 examples, I'm going to give 6 in this video. Persevere with it, keep trying, and I'm hoping you will be convinced and converted that this is the way to go for integration by parts. So let's start with worked examples. First of all, found the integral of ln x dx and have highlighted this as an absolute must-know. You're probably thinking, well, how on earth is this integration by parts? It's not even a product, it's just ln x. Well, this is the why it's a must-know, because essentially it's a very subtle manipulation. What we need to do here is we think of ln x as ln x multiplied by 1. So I'm going to show you now how this DI table works. So we consider this as ln x multiplied by 1 dx. So think about the LIAT acronym. So L is logs. Do we have a log function? Yes, we do. It's ln x, so we stick ln x in the D column. In the I column, we're going to put 1. So the D column, let's differentiate. Ln x goes to 1 over x. 1 integrates to x. As I mentioned with the instructions and the method, you stop when you can integrate a row. So look at this row, take the product of these two. 1 over x multiplied by x is just 1. Can we integrate 1? Yes, we can. So I'm going to stop at that row. I'm going to underline it in red. We multiply the diagonals, like I said in the instructions, not instructions, rather the method, and we keep multiplying diagonally down until we touch an entry which is in the final row. So we do ln x, I'm going to multiply that with the x sits in the final row, and so that's the only diagonal product I'm going to take. So therefore this integral becomes x times ln x. Then I take the integral of the final row. So I've got minus 1 over x multiplied by x, this product with respect to x. So because it's a minus 1 over x, I'm going to put minus 1 over x multiplied by x dx. So I have x ln x. That's just, of course, going to be the integral of 1 dx. So finally, x ln x, 1 integrates to x, so I'll get minus x, plus, of course, the constant of integration, plus c. So the final result is this. Second worked example, integrate x cosine x dx. Again, think of Layat. What comes first in Layat, the algebraic expression or the trig expression? Well, a comes before t in Layat because a takes precedent and the algebraic function is x. We put x in the d column. Therefore, in the other, it's got to be cosine x. So differentiate the d column. X goes to 1. You can differentiate again if you really want to. 1 would differentiate down to 0. Cosine would actually integrate to positive sine. And if you wanted to go again, you could. Sine would integrate to minus cos. Sometimes you can just keep going if you really want to. Sometimes it's useful, sometimes it's overkill. Anyhow, let's think about what our final row would be. Looking at the second row, minus 1 multiplied by sine x minus sine x. Can we integrate that? Well, yes, we can, or at least you should be thinking you can. That's a very simple standard result. So I'm going to stop at that row because that definitely is one we can integrate. So we're going to do the product of x multiplied by sine x. That's the only diagonal product we're going to take because sine x is an entry in the final row. So therefore, x cosine dx becomes x multiplied by sine x, and then the integral of minus 1 multiplied by sine x, that's going to be minus simply the integral of sine x dx. That's going to give x sine x. This is why sometimes going a bit further is helpful, because we can see now the integral of sine is negative cos. So we're going to get minus cosine x. Then, of course, the constant of integration, which we'll always need to consider when taking a indefinite integral. And simplifying this down, that's going to give us x sine x minus a minus becomes plus cosine x plus c. I'm hoping now it's slowly starting to click. Let's have a look at a third example. The integral of x squared ln x dx. Again, what do we put first? Think about that Layat acronym. So logs, L comes first, therefore we put D as ln x. Because A comes after L in the Layat expression, I'm going to put x squared in the integral column. So I need to differentiate ln x, which gives me 1 over x, and then I need to integrate x squared. X squared obviously integrates to 1/3 x cubed. So is that going to be our final row? We'll take the product of it. Minus 1 over x times 1/3 x cubed. That'll give us minus 1/3 x squared. Can we integrate something which is just a constant times x squared? Yes, we can. So that's our final row. If you're thinking of any other seems to be 2 rows, just wait till example 4 and certainly example 6. So what we're going to do here, we're going to take the product of ln x and 1/3 x cubed, and then afterwards that's going to be our final and only diagonal product, because 1/3 x cubed is an entry in our final row. So therefore this here is going to be 1/3 x cubed multiplied by ln x. Then the integral of this is going to be minus, it's a minus 1/x, 1/x multiplied by 1/3 x cubed dx. So that's 1/3 x cubed ln x. I can take this 1/3 to the outside of the integral. That's going to give me x squared dx. Simplifying next, I've got 1/3 x cubed ln x minus 1/3 x squared integrates to 1/3 x cubed, plus of course the constant of integration. And finally, to simplify, I'll get my underlining ready. That then gives me 1/3 x cubed ln x. 1/3 times 1/3 is a ninth, so I've got minus 1/9 x cubed plus c. Let's have a look at another one, worked example 4. Find the integral of x squared e to the 3x with respect to x. So, LIAT. Again, algebra, algebraic, exponential. A comes before e comes last, so we're putting x squared in the d column. Therefore, in the I column, I'm going to put e to the 3x. Let's differentiate x squared. We get 2x. If we integrate e to the 3x, that 3 comes to the front and we divide by that 3, so we get 1/3. The power stays locked. We can't increase the power when we integrate an exponential, so that's going to give 1/3 e to the 3x. Look at this row. Is this our final row? Can we integrate this? Well, we're trying to integrate a product of 2x and 1/3 e to the 3x. Do we know how to do that? I don't think we do. So actually, this is where we need to go again. So one more row. Differentiate 2x, gives us 2. Integrate 1/3 e to the 3x. Again, in the same way as before, the 3 will drop to the front and we end up dividing by the 3. So 1/3 divided by another 3 becomes 1/9. So we get 1/9 e to the 3x. Is that our final row? Well, can we integrate 2/9, some constant of e to the kx? Yes, we can. So that's our final row now. So I can underline this one. So therefore, we need to take two diagonal products. We're going to go x squared multiplied by 1/3 x cubed. Then we're going to have minus 2x multiplied by 1/9 e to the 3x. And then we integrate this final row because we can integrate this without much trouble. So the product of the first diagonal, that's going to give us 1/3 x squared e to the 3x. Then this 2x, consider that minus is attached to it. So I've got minus 2x multiplied by 1/9 e to the 3x. Hence minus 2/9 x e to the 3x. And then we're going to take the integral of this final row. So we're going to integrate, positive integral, 2/9 e to the 3x. So I'm going to sort of skip a step ever so slightly. It's a fairly small step I'm going to be skipping. Rather than integrating 2/9 e to the 3x, I'm going to take the 2/9 to the outside immediately. So it's going to be 2/9 integral e to the 3x with respect to x. So this one's already sorted, these two products I can just leave as is. So it's just a case of thinking about what e to the 3x would integrate to. I'm going to have 2/9, of course. E to the 3x, the 3 comes to the front, end up dividing by the 3, so we get 1/3 e to the 3x. Then don't forget that pesky constant of integration. So finally, just neaten up and we're done. So this is going to become 1/3 x squared e to the 3x minus 2/9 single x e to the 3x plus 2/9 multiplied by 1/3, which becomes 2/27 e to the 3x plus c. So it also works, this DA method, very much the same for definite integrals as well. So after integrating the final row indefinitely, we can simplify the expression to be integrated and then afterwards apply the limits of integration just once to what we've got. So this worked example 5 I've basically lifted from a past paper. There's a similar one in the Edexcel book too. The book explains it well using the traditional method which I was taught, which by showing you this method I am not trying in any way, shape or form to belittle. I just prefer this method. I think it's, as I've said before, to use a term, a game changer. So this one, part A, use integration by parts or otherwise. I'm not going to do the otherwise, just let's focus on the integration by parts. Find the integral of the product of x minus 1 multiplied by the root of 5 minus x dx. I'm just going to rewrite this in power form. I'm going to write it as x minus 1, 5 minus x to the 1/2 dx. So let's think about what Layat tells us. So there's definitely no log expressions there. A, well, both of these are A. That's algebraic, and this is algebraic too. So which one do we go for? How do we know? Well, the general rule is put in the D column the one which will easier and quicker differentiate down to 0 eventually if needed. So the easier one to differentiate would be x minus 1. X minus 1 would differentiate to 1, which would differentiate down to 0. In the integral column, I'm going to put 5 minus x to the half. So integrating 5 minus x to the half. If you're a bit shaky or unsure how to do this, because it looks a bit harder than just integrating x to the half, this essentially is the chain rule. This is the chain rule. I thought I was losing my mind. I'm not. I'm not going to show you how to do it here. That can be your own research. But if you were to set u, for example, to be 5 minus x, du by dx would be minus 1, because we've got a minus x essentially. It's going to integrate similar to if it were positive x, but then we're going to get a minus on the outside. So what's going to happen here? I'm going to get 5 minus x. Obviously the power, 1/2, we're going to add 1 to that, so that becomes 3/2. And then we divide by the new power like we normally would anyway. And so the 3/2 dividing by 3/2 is the same as multiplying by 2/3. And so essentially what we're going to have here is 2/3 first. However, because it was the minus x, that actually gives us minus 2/3, like so. So this row here, could we integrate this row? Well, this row, minus 1 times minus 2/3, it's just a positive constant, then integrating 5 minus x to some power. Well, if we can integrate this one, which we just did to get there, we certainly could integrate this as well if we needed. So that's our final row. We just need 2 rows. So for part A, we're just going to do one diagonal and take the integral of the final row. And so for A, that's the same as the product of x minus 1 multiplied by minus 2/3, 5 minus x to the 3/2, which is minus 2/3 x minus 1, 5 minus x to the 3/2, and then the integral of a product of this final row. So it's going to be minus 1 times minus 2/3, so plus 2/3 of the integral 5 minus x to the 3 over 2 dx. So this bit we can stay as it is. X minus 1, 5 minus x to the 3 over 2. This here, I'm going to get 2/3 multiplied by what we get to integrate this, plus, of course, the constant of integration at the end. So, integrating 5 minus x to the 3 over 2 is going to be really similar to integrating 5 minus x to the power half. So, again, the power will increase by 1, so the new power will be 5 over 2. So we're going to have 5 minus x to the 5 over 2. And then we're going to divide by the new power. So we're going to divide by 2/5. But in the same way as we saw before, if you're not sure or convinced by what I'm saying, please try the reverse chain rule yourself or use a U-sub. This, because it's a minus x, we'd actually put minus 2/5 first. So then we get minus 2/3 x minus 1, 5 minus x to the 3 over 2. 2/3 multiplied by negative 2/5. That's going to give minus 4 over 15. So we have minus 4 over 15, 5 minus x to the 5 over 2 plus c. So that's our answer for part A. For part B, where we need to find this integral here, oops, I'm just going to section this out so that it doesn't get confused with part A. So if I just leave that there, so part B, this integral is now between limits of 5 and 1. So we can take our result from part A, and then we don't need to think about the positive constant of integration. So this here we can just put the limits in straight away. So it's going to be minus 2/3 x minus 1. Don't know what I was going to type there. Sorry, x minus 1, 5 minus x to the 3 over 2, minus 4/15, 5 minus x to the 5 over 2, between the limits of 5 and the lower limit of 1. So if we input the upper limit, so what happens when x is 5? Well, minus 2/3 times blah times 5 minus 5, this is going to become 0. So because we've got 0 to this power, it's just going to be 0. Okay, so that's going to be 0. Then we minus off 4/15 of 5 minus 5. So again, we're going to get 0. So inputting 5, the upper limit, is very nice. It's just going to be nothing. Then minus what we get when we input the lower limit of 1. If I input 1 into this first expression, because I've got x minus 1 here, it's going to be minus 2/3 times a whatever times by 0. So the first bit's going to be 0 again. Over here, I'm going to have minus 4/15, and now I'm not going to get a 0. I'm going to get 5 minus 1, which is 4, to the power 5 over 2. So that's going to simplify. That's just nothing. Minus a minus is a plus, so I get 4/15 multiplied by 4 to the power 5 over 2. Obviously use your calculator if in doubt, but this is quite a nice GCSE or pre-GCSE question. So I can take 4 to the power half, the square root of 4, which is 2, and that to the power 5 is 32. 2 times 2 times 2 times 2 times 2 is 32. So in exact form, 4 times 32 is 128 over 15. And my suggestion would be to check this on your calculator. So I think it's worth me just briefly building in a bit more time on this video to just show you how to check it. So get your calculator ready. Yours might look different to mine, but it should have this function built in anyhow. On mine, we have an integral button here, so I'm going to input the higher limit of 5, the lower limit of 1, and then the first bit was x minus 1, so alpha x minus 1, close bracket, open bracket, 5 minus x, so 5 minus alpha, press that bracket, close brackets, and then because it's a square root, I'm going to say it's to the power of a half. So press equals and let the calculator do some thinking. Your calculator will be integrating numerically here. So it's thinking, it's number crunching behind the scenes, and it's coming out 8.533333, which is different certainly to what I put, which was 128 over 15. So to check that, if I just put 8.5 in definite threes, you can see it comes out to be exactly correct. So we are right. We're exact, actually. The calculator had truncated the decimal. So actually, in this particular example, we're better than the calculator. Go us. A final worked example, a repeated row. This is an extension. I first came across these doing further maths, and then again at university. These are particularly satisfying, I think. So find the integral of sine x e to the x dx. So I'm going to call that I. That's our integral. Why am I calling this I, and I'm not called any others I? You'll see why in a moment. So, Liat. Right at the bottom of the list, Liat is exponential functions. So, trig, t comes before e in Liat, so I'm going to put d as sine x e to the x in the I column. If I differentiate sine, I get cos, integrate e to the x, it just gets itself. If I differentiate cosine x, cosine differentiates to negative sine. I'm going again for another row, by the way, because cosine x times e to the x is no easier for me to solve than sine x e to the x. So this one we can't do. So that's how I'm going to go again. So e to the x integrates again to e to the x. Now this is when you need to remember one of those extra things I mentioned in the method. You stop and take as your final row. If it's not a row that can be integrated, you can also stop if you see a multiple of a previous row. The first row was sine x e to the x. This row here, plus times minus, is minus sine x e to the x. So this row is minus 1 multiplied by the first. So because this is a multiple of the first row, we can stop here. That's our final row. So we've got two diagonal products to take before we end up touching a entry on the final row. So we're going to do this one and that one. So I, the integral of sine x e to the x, is going to be sine x times e to the x. I'm going to write e to the x first. E to the x times sine x. Then minus cosine x times e to the x. That's minus ex cosine x. Then I'm going to take this product and integrate. So then it's going to be minus the integral of sine x e to the x. So minus sine x e to the x dx. But if I think about what sine x e to the x dx actually is, then that's our original question, which is I. So I can rewrite this as I equals e to the x, which can factorize out now, because I've got this twice. So e to the x sine x minus cosine x minus I itself. So now I can rearrange this like an equation. So if I add I to both sides, I get that two lots of my integral, two lots of big I, is e to the x sine x minus cosine x, and simply divide both sides by 2. I therefore see that the integral which we defined to do this, is just going to be 1/2 of e to the x multiplied by sine x minus cosine x. A thing of beauty. And there we have it. I do hope those 6 warm-up examples, and sorry, worked examples rather, I mean to say, have helped to convince you that this method might be a powerful tool to be using, even though the instructions of the method and explaining it just seems rather bizarre. It really is a powerful tool and can simplify and speed up your integration by parts. So I hope you found that useful. As I say, now though, it's over to you to get some practice in. The questions I'm going to suggest you attempt, essentially, are all of them from exercise 11F in your lovely blue book, page 309 to 310. Try all the questions. This is a skill you really need to hammer again and again and again. Good luck. You know where to find me if you need any help. Keep plugging away, and I'll see you all soon.